All right, round two. So we last time talked about point to point, point to plane, point to line distances, right? These three, what's nice about these is these are solved by three of our most fundamental vector operations, right? Vector magnitude, vector dot product, and vector cross product are the tools that solve each of those problems, right? You have point to plane, and point to line. Those three formulas, right? These are exactly the um, right magnitude, dot, and cross, right? That's what answers those first three distance questions. Now, it turns out, and here I have just those results. See the previous video if you want to see where these formulas come from, right? But these are the super condensed summaries of just diagram formula, and that's it, right? So um, this video is where I fill in the claim that these later cases, line to plane, plane to plane, and line to line, that these somehow reduce to these earlier cases, right? Case one, two, and three. So let's talk about how. So let's start with case four. So case four, line to plane, right? What happens there? So first thing to notice, of course, is if they intersect, then the answer is just zero, right? Then the distance is zero. That's always the case with any of these, um, right? We always say that the two objects are of distance zero if they intersect, right? So if the line actually intersects the plane anywhere, then the distance between them is zero. Um, and on the other hand, though, if they don't intersect, then we have some work to do, right? Because then there is going to be a non-zero distance. So imagine you have non-intersecting. Well, if they don't intersect, then what must be the case? What must be the case is that you have some line, right, that's running parallel to the plane, right? So I have my plane down below, then I have my line up above. Well, what must be the case, right? Otherwise, um, you can actually pick just pick any point on the line and then do the point to plane formula, right? Because it doesn't matter, if I pick P1 or if I pick P2, right? If the line and plane aren't intersecting, then the distance of P1 to the plane or the distance of P2 to the plane, right? Those are going to be exactly the same. Because if those distances were different, then it means the line is, on a collision course with the plane and it will intersect somewhere, right? So that's the manner in which line to plane reduces to the point to plane case, right? So we essentially already solved line to plane when we solved point to plane. Very nice. Okay, what about plane to plane? So plane to plane, once again, if they intersect, then the distance is zero, right? But otherwise, if the two planes do not intersect, well then same thing, right? Just reduce back to the point to plane formula because again, if you have planes that do not intersect, right, then you can imagine, okay, there's one plane, there's another plane, right, and they don't intersect. They have exactly the same normal vectors, right? Then what you can do, you can just pick um, literally any point on the top plane, right? And then just do point to plane, right? Pick one plane, pick your favorite point in that plane, and then do point to plane down to the other one, right? And then so just go find that distance and you're done, right? So this case we also kind of did already, right? The point to plane again will knock it out for you, right? Okay, there's a reason I wrote this one last. This one is by far the most complicated. So line to line. Well, again, if intersecting, right? Distance zero, right? Same. That story is still the same. Um, and if they're parallel, right? If your two lines are parallel, then use the point to line, right? Again, it's kind of already solved, but this time by a different formula, right? So if you have two parallel lines, right? L1 and L2, and they're parallel, meaning their direction vectors are parallel or even equal, right? So they never intersect in the sense that they're parallel. Then you can just do the point to line distance formula, right? Pick your favorite point P on one line and then just do the distance to the other line. Because again, if they're parallel, it doesn't matter what point you pick on one line, it'll always be the same distance to the other line. Okay. But here we go. There's a catch. There is a way in 3 dimensions. There's something that can happen that cannot happen in 2 dimensions. You can have skew lines. What are skew lines? Skew means they're not intersecting and they're not parallel. So this is what skew means. They're not intersecting, but also not parallel. Right. So it might take a second to visualize this. Because in the plane you can't have this, right? In the plane, if two lines don't intersect, they're automatically parallel in the Euclidean plane, right? If you're in 3 dimensions, if you're in R3, this is no longer the case. There are 3 different things that a pair of lines can do. They can intersect, they can be parallel, or they can not intersect but also not be parallel. How so? Well, here's, I think, a good way to visualize it. If you're sitting in a room and the room is a boxy shaped room, right? Look at the crack that the floor makes with the wall in front of you. Look at that line, right? That's a line, that crack, that corner. So that corner with that line, you can see all 3 of these cases in the room. If you look at the crack of the ceiling that make the front wall and the ceiling, that would be parallel to that ground initial floor crack, right? If you follow that ground floor crack in front of you over to, say, the left intersection, the left wall, right? And then that vertical crack, that's a line that's intersecting, right? But then say the back wall, right? The vertical crack along the left back wall, that will be a line that's skew, right? It's not parallel, but also not intersecting. So to draw this out a little more, um, to not just do it in words, but to see it in a drawing, right? What I'm saying here is, if you think about a box, right? I think just the sides of a rectangular prism is probably the easiest way to see skew lines, right? So what I'm saying here is we're sitting in a room, right? So we're sitting in a room here, and so we're looking, we're sitting here in our chair, right? And we're looking this way. So here, right, I'm looking at this crack in front of me. right? This is parallel to the floor and the ceiling. Give me two parallel lines, right? But then the floor and the left wall, this is the example I was saying before, give me a pair of intersecting lines. But then the floor, that same floor crack, right, and the back left vertical, right? Those, they're not intersecting and they're not parallel, right? Those give me a pair of skew lines. Okay, so let's now um, talk about the skew case, right? Intersecting is easy, just distance zero. Parallel, go use point to line. We already figured that out, right? But skew, we actually need something different. So I think this little room configuration is actually the perfect way to see how to solve the skew case, because you can actually see the answer here in this box, right? The distance between this pair of skew lines, it's actually this distance right here, right? It's the length of that crack that connects them, right? So what you need is you really need the you want to take this line, the one skew line, take its direction vector, and then take this other line and take its direction vector, and then take their cross product to get the direction of their distance, right? And in fact, this is going to be the normal vector for this pair of parallel planes that contain these skew lines, right? Right, this plane and this plane, that's a pair of parallel planes picked by Peter Piper, that contain the pair of skew lines, right? And you can get their normal vector, right? The normal vector for their for that parallel planes, right? So if skew, then calculate their normal vector using the cross product of the two lines, right? And then once you have that normal vector, then you can do, pick P. So then, um, then do point to plane, right? Because see, now you have enough information. What point and what plane? So do point to plane using any point P on the one line, right? And then use any point Q on this line along with that normal vector, that gray normal vector, right? Because Q, any point from the second line, along with N, will together specify that plane, right? And then we're just doing point to plane distance with any point P from the first line, right? So that's our third case for line to line, right? So that's probably the trickiest case of all of these. All right, so there are the formulas. Right, notice once again my claim in each case, it somehow reduces, it's either zero or it's a previous formula, right? So it's either point to plane, point to line, point to plane, or point to plane, right? So most of the time it's point to plane, and in one case it's point to line, right? So that's the way in which these cases 4, 5, and 6 reduce these earlier cases 1, 2, and 3, right? Um, example, let's do an example. So, um, for example, let's say, the, let's find the distance between the lines let's see, t, 1 plus 2t, and 0. And let's do um, -1/2. t, negative t, 2. All right, let's do those. Let's do those two lines. The distance between those two lines. Okay. So as you noticed here, when we describe this, it really depends about the geometry of those lines, what method we do. Are they intersecting? In which case it's just 0. Are they parallel? In which case we use point to line. Or are they skew? In which case we use point to plane after doing a cross product, right? So let's figure this out. So first question, do these intersect, right? Do these intersect? No, because this z coordinate is always 0 and this z coordinate is always 2, right? So in this case, no, they're not intersecting. They never have the same z coordinate, right? Okay. Now, are they parallel? Right? Are they parallel? So what I need to do is I need to ask what is the direction vector for each line, right? So the direction vector is going to be given by the coefficients of t, right? So for line 1 and line 2, here are the coefficients of t, right? Now, do I need these to be equal for them to be parallel? No, I just need for them to be scalar multiples of each other. I just need for them to be parallel, right? So here I could say, notice d1 is actually negative 2 times d2, right? There we go. Cool. So yes, they're parallel, right? So yes, they are parallel. There we go. So here then is our method, right? What do I want to do? I want to take, I have parallel lines, right? So I want to use the point to line formula, right? Because I have this L1 and L2 are parallel, right? So I'm going to take any point at all on L1. So I'm going to use P. In this case, I'll use 0, 1, 0, right? And then Q, I'm going to use as a point on the other line, which here I'll use 0, 0, 2, right? So I'm just plugging in t equals 0 to get some point on each line, right? So there's my P and Q. And you don't have to plug in t equals 0. You plug in t equals literally anything, right? I'm just using 0 because it's easy. And then I'll use d2, right? I'll use the vector, the direction vector d2. Okay. So now I use that point to line formula, right? So how do I get this distance, right? Given that information, what do? For point to line, I use cross product, right? Point to plane is dot product. Point to line is cross product. This cross product ends up pretty clean because there's a whole lot of zeros, right? And then I do the sum of squares of the coordinates d2 down below. Take the square root of that, right? So once again, now up here for this cross product is just 2, right? Because you have a 0 on every single, you do all the little x's, but you have a 0 on every single factor except for that one, right? So 2 is the only non-zero term in this cross product. And then in the denominator, I have what? I have root 5/4 right? So this is 2 over root 5 over 2. So I get 4 over root 5. So I get 4 root 5 over 5, and there we go. There is our distance between those lines. Fine. My Tori came to help check my crush project. So thank you. You're good at catching minus sign errors and crickets, both of those. All right, so there's our line to line distance formula. Okay, then what do we have next? Let's do another example, right? Just there are so many cases here, right? So let's do another example. Let's do another this. Let's say we had oh, you really want to be involved in that? Oh, yes, you can, of course. So find the distance between these lines. She thought I said find the distance between the lions. She's like, I'm a lion. I'm a lion. All right, so find the distance between what lines? L1 given by, let's do lines given in symmetric form this time instead. And same with L2. Let's do the first line is going to be x 2 times y minus 1 and z. Those three quantities are all equal. That's what will determine the first line. Right. The second line will be x minus 1 equals y over 2 equals, let's do z plus 2 over 2. Or let's say over 4. There we go. Over 4. So there we go. There we have our two lines, right? So we have the distance between these two lines in symmetric form. All right. Next, let's think about what case are we in? Are they parallel, intersecting, or skew, right? So here, it's pretty easy to see that they're intersecting, right? So in this case, I claim the answer is 0, right? Because they intersect. Right, and how can I determine that, right? This is here, there's no tricky vector geometry to do in terms of cross products or dot products or anything. We don't even get that far, right? They're just intersecting. But how would I determine that? How would I know that they're intersecting, right? There are different ways to go. But I think probably the easiest way to go here is just good old substitution, because the lines are given in symmetric form, right? So what you could do is you could say, consider them as a system of equations, right? We're looking for a solution to it as a system of simultaneous equations, right? And how many equations do we actually have? We have 4 equations, right? Why? 1, 2, 3, 4, right? I have 4 equations, 4 equal signs, right? So this is why most of the time lines don't intersect in 3D, right? If you pick 2 lines at random, the probability of them intersecting is very low, right? Because you have 3 free parameters. You have 3 unknowns, x, y, and z, but you have 4 equations, right? So intersecting is very rare. But how could you determine this? Well, write it down as a system of equations, like I said. So consider equation 1 to be x equals 2 times y minus 1. Consider equation 2 to be the next one, 2 times y minus 1 equals z. Consider equation 3 to be x minus 1 equals y over 2. And consider equation 4 to be z plus 2 over 4 equals y over 2, right? So here I broke them apart, broke them out of this symmetric form and put them in more normal, like list of equations kind of form, right? The symmetric form is a little wonky, right? Because you're kind of listing two equations all in one big string. But put them sort of more traditionally how you'd write equations in college algebra and pre-calc, right? So here's our little system of equations. Well, now you can just use substitution, right? So I can say, all right, if I sub, for example, from equation 1 into equation 3, right, I'm going to be able to solve for y. So let's do that. So I get, what would this become? I would get 2y minus 2 minus 1 equals y over 2, right? Get rid of the fractions. So I get 4y minus 6 equals y, right? And then what do I have from there? Then I'm going to get 3y equals 6. So I'm going to get y equals 2. There we go. So I got a numerical value for y. And now plug that back into, say, equation 2, right? Now that we found that, sub that into equation 2. And what do I get? I get z equals 2 times 2 minus 1. So just 2. Okay. All right. So see these three equations, this was three equations and three unknowns, right? So that's why we already fully solved the system at this point, just using these three equations. So now if you take those numbers that we got and plug them into equation 4, see most of the time, equation 4 is you'll get a contradiction. You'll get two quantities that are not equal, right? But here you actually do, because here I'm going to put z equals 2 and y equals 2. And I want to know, are they equal? And yes, this is true, right? This says 1 equals 1. Right. So this does actually solve all four of our equations. Oh, and we can check equation 1 too. We didn't actually say what x was, right? Once you have y or z, you can plug back in and get x. What is x here? X is also 2, right? Right, if you look up here, if you plug in y, right, you also get x equals 2. We didn't need x when we checked equation 4, but x is also 2, right? So what does it mean? It means that the point 2, 2, 2 lies on both lines. Right, so that's why the answer here is 0, because the lines intersect. Right, so there we go. So there's an example of finding a distance in a case where the lines are parallel. Right, here's an example of finding a distance in a case where lines are intersecting. So one of each. Let's do one skew example before we call it. So here I'm told you up front the lines will be skew, right? So here I'm not doing examples of cases 4 and 5, right? Those are honestly a little bit simpler. So I'm really focusing on case 6. The line to line is the weirdest one. So that's why I'm doing 3 examples on case 6. So let's do this. So let's find the distance between, and let's see, we did one in parametric form, we did one in standard form. Let's go back to parametric form, right? So let's do another one in parametric form. So the lines L1 and L2 and there we go. There we have our 2 lines, right? So here This is actually I claim these are skewed, right? But let's not just take my word for it, right? Let's actually figure this out. So um, let's ask first, are they intersecting? Right? Are these lines intersecting? So how could you do this? Well, set the x coordinates equal, right? Set the y coordinates equal, and set the z coordinates equal, and then solve it like a system of equations. Except, here's what you have to use two different parameters, right? Like don't just leave it all as t, because the the two lines don't have to intersect. They have to share the x, the y, and the z value, but they don't have to intersect the same t value. Like t equals 1 on this line maybe gives you the same point, the same x, y, and z as t equals -3 on that line or something. It doesn't here in this case. I'm just saying hypothetically, right? So that's why you have to call it when if you're solving for an equality between two parametric formulas, you have to pick different parameters. You can't just leave it as t, right? Because then you're assuming that the parameter is equal. You might miss an intersection point. So so here we go. Again, whether you're in symmetric form or whether you're in parametric form, again, um, we have more equations than unknowns, right? Here we have three equations, but only two unknowns. So it's similar idea of why lines usually don't intersect, right? So this is here we have our two equations and two unknowns, right? So let's look at these. We'll solve these and then we'll plug into the third one and see if it works, right? So here, if I solve these, the first one's already solved for t1, the first equation. So take that and plug it in here, right? Just do substitution right there. And so what do I get? I get that becomes 1 minus 1 cancels, and then I have just negative t2 equals 2t2. So I get t2 equals 0, right? So t2 is 0, which then if I come back up here, then I know t1 equals 1. Okay, so if these lines intersect, it's going to be at parameter 1 for the first line and parameter value 0 for the second line. But if you plug those into this third equation, it doesn't hold water, right? In the third equation now, try this t1 value is 2 times 1, but that is not equal to what you get if you plug in 0 for t2, right? Those are not equal. So no, they're not intersecting, right? Okay, they're also not parallel, right? Because what do I have here? I have the direction vectors are just the coefficients on t, right? The first line has direction vector 1 minus 1, 2. The second line has direction vector 1, 2, minus 1. And those are not scalar multiples of each other, right? These are not parallel. Those are pointing totally different directions. There's no scalar times d1 that equals d2 or vice versa, right? Or you can take their cross product and see that their cross product is non-zero. Either one. Okay, so what do I do instead? Now we're up here in this skew line case, right? Now I really know that I have skew lines, so we're going to do this construction. I'm going to take their cross product to get the normal vector for the pair of parallel planes containing the lines. Right? Okay, so let's do that. So I have a normal vector, right? Is going to be what? It's their cross product. So let's do our little cross product. So I get 1 minus 4 in the x, right? I get in the y, I get 2 plus 1. And in the z, I get 2 plus 1. So there we go. So I get minus 3, 3, 3. Right, there's my my cross product of those two direction vectors, right? So now I can say for these lines, right? I have, so again, just to get the diagram here. So here's line L1, and line L1 contains the point 0, 1, 0, right? So I'll say P equals 0, 1, 0. And it had direction vector D1, right? Then I had, down here I had, well, it's not really below it per se, but this is a somewhat abstract representation. Because we don't need a really precise representation here. I just need to show that they're not parallel and not intersecting. So then I have this line L2, and I have this, what's my starting point for L2? And what do I mean by starting point? Just a line doesn't really have a starting point, but I just mean plug in zero, right? Just zero parameter value. So 1, 0, 0 for L2. And then and then we have this direction vector, D2, right? And then we took the cross product to get this N, right? So now I have this normal vector that gives me a plane, right? That is that line L2 is contained in that plane, and line L1 is parallel to that plane, right? And if you want, you could think of there's another copy of that plane that contains L1 that's parallel to it, or you could just think of it as the line is parallel to the plane. Either way, totally valid. Either way, we're going to do point to plane on this new plane using point P, right? So that's going to give us our result. So let's do the point to plane distance. So point to plane is where we use dot product, right? So I'm going to do PQ dot D2 over magnitude of D2. Right, so take P minus Q, right, and then take D2, right, we're going to dot it with D2. Sum of squares, there we go. And what do we get? We get -1 plus 2 up top. I get root 6 in the bottom. So I get 3 over root 6. So I get 3 root 6 over 6. And this gives me root 6 over 2 as my result. There we go. Right, that is the distance between the lines. Okay, we got it. Right, so that's definitely the hardest case of this line-to-line distance in the skew case. But notice it still reduces to our essentially a dot product calculation, right, when it's all done. So this, I guess, to be honest, though, we had to use cross and dot in the skew line case, right? Because you have to use cross to get the normal vector, right? And then you use dot to get the distance in the point to line, the point to plane distance calculation. So, all right. Thank you to my cat Annie for credit where credit's due, getting me through that calculation, helping us check our minus signs there. So, all right. Thanks so much.